Okay, well, last time we introduced charges and materials that either allow charges to flow, conductors, or prevent them from flowing, insulators. But what we'd like to do, and what we will do today, is describe the forces on charges that would cause them to move. Okay, so that's Coulomb's law. We'll introduce this and try to get an understanding for the forces that objects feel, charged objects feel, in the presence of other charged objects. And then what we're going to do is we're going to abstract away the charge that's feeling that force and try to understand what the distribution of charges around it does to produce something that will move the charge. So that's the electric field. So that's where we're going. And to start with, we can describe the force on a charged object using Coulomb's law, shown here. Let's see if I can. Pointer doesn't show up. Okay, so the force on the electrical force on an object, that's what this little E stands for, is proportional to, and this K is a constant of proportionality, the magnitude of our first charge times the magnitude of a second charge. There has to be more than one charge interacting in order for there to be a force between them. So Q1 and Q2 are the magnitude of the two charges and inversely proportional to their separation squared. So if we bring two charges closer together, they will exert a stronger force on each other. And if we move them further apart, that force will be weaker. And then this little thing here, r hat, that's a unit vector that just means away from each other. That's all that means, okay? So the electric force on a charged object, Q1, due to another charged object, Q2, is proportional to the product of their charges. It's inversely proportional to their separation squared, and it points outwards. Okay, that's what that says. Now, it points outwards if Q1 and Q2 have the same sign, because then this becomes positive. But what if they're opposite sign? What does this equation tell us? Would this be a positive or a negative quantity if Q1 and Q2 are opposite in sign? It would be negative. Okay, so we'd have a negative, and the direction is outwards. So what direction is negative outwards? Vincent? It would be inwards, right. Okay, so opposite charges attract. Like charges repel. It's just another way of saying that mathematically. Now, a little bit of note-taking to clean up a few things that I said. This constant of proportionality, K, we can introduce it this way, although we usually represent that constant in terms of a different constant, epsilon naught. And so K is equivalent to 1 over 4 pi epsilon naught. And we'll introduce what this term epsilon naught means in a later lecture. And when we go over Gauss's law in chapter 6, it'll become obvious why we express it in terms of this funny 1 over 4 pi. The geometry of some of the other equations that will have that constant in it have 4 pi come out of the geometry. And by using this 1 over 4 pi epsilon naught, those 4 pi's cancel, and a lot of things will work out easier later on. But for now, we can either just call it K, which has a magnitude of 8.988 times 10 to the 9 Newton meter squared per Coulomb squared. We know the force we want to measure in newtons in SI units. And the charge, now we're going to measure in units of Coulomb. So Coulomb is the scientist who quantified this law, and so he gets the unit of charge named after him. And R is going to be measured in meters. So just some dimensional analysis tells us in order for this to end up in newtons, if Q1 and Q2 are in coulombs and R is in meters, K has to have units of newtons, meters squared per Coulomb squared. Okay, so we introduced a unit of charge last time, called E, the fundamental unit of charge, or the fundamental element. And we said that objects were made of atoms, and atoms have protons and electrons in them. And each proton has a charge of plus E, and electrons have a charge of minus E. So it's the elemental unit of charge, and everything has some integer number of E. Well, it turns out electrons and protons are really small. And so if we're talking about atoms, it makes sense to talk about electrons and protons being the charged objects. But when we actually have like a macroscopic object that's charged up, there are so many electrons and so many protons that the unit of E is not a very useful unit of charge. In fact, this Coulomb that we plug in here has about 6 times 10 to the 18 elemental units of charge in it. So it's hugely bigger than just a single charge. Okay, or another way of saying that is if we solve for how big 1e is, 1e is about 1.6 times 10 to the minus 19 coulombs. Okay, so an individual electron or an individual proton has a very, very small charge when measured in coulombs. Okay, so coulombs is the SI unit of charge. Does this equation look familiar at all? Can anyone think of an equation that looks very similar to this that you might have learned last semester? Yeah. Yeah, good. Newton's universal gravitational law looks almost identical, right? This was a measurement of the force of gravity between two massive objects, m1 and m2. There was this constant of proportionality, and there was this inverse distance squared dependence. The difference is this had a minus sign in it, so it was always pointing inwards. And these are very analogous, right? If we just replace m with q and k with minus g, these are the same. But what's different about mass compared to charge in these equations? Yeah. Mass is always positive. We don't have negative mass objects, so we can't get this product to be negative. We can't get masses to repel each other. But charges can be positive or negative, so they can attract or repel. Otherwise, these equations are equivalent. Okay, so what we're going to do is just use this conceptual idea that the force is proportional to the charge, to the product of the charges and their separation squared. And we're going to do a little activity. I want you to work in small groups of about 5 students, 4 to 5 students. And I want you to try to agree on an ordering for these 6 charge distributions, A, B, C, D, E, and F. And what we're trying to order them by is how big is the charge, or is the force on this positive test charge up here, Q test. And in every scenario, we have that same test charge sitting at the same point. But here there's some net 3Q of charge, okay? So 3 times as much charge as we have here. This is minus Q, so this is the opposite sign, and is 3 times smaller than that. This has the plus 3Q and a minus Q up here. And then these have 3 positive charges that are acting on this positive test charge. So try to figure out which of these positive test charges feels the greatest force and which one feels the least force, and in between come up with an ordering. Okay, can we work together as a class with what you've discussed as small groups to see if we can come to a consensus? Let's start with the least. Does anybody want to suggest one of these scenarios that they think has the least magnitude of force on the test charge? Yeah. E and D. B and D. Okay, B and D. So do they have the same force on them? Okay. So how do we know they have the same force on the test charge? Okay, so there's only one other charge present. It's the same distance away in both cases. And what about its magnitude? The magnitude's the same, right? Just one's positive and one's negative, right? So this has a repulsive force, and this one has an attractive force, but they should be the same magnitude. Okay, so like, why is that going to be less than, for example, A? I'll let someone else take this out on. How do we know, for example, that D, this charge feels less force than this charge? Yeah. Yeah, this is a greater charge here. It's 3 times bigger, so it's going to produce 3 times as much force. Okay, so let's do the other end of the spectrum. Which of these has the greatest force on the test charge? C. Okay, so why C? Okay, so we have some repulsive force from the 3q charge down here, and this minus q, what does that do? It attracts it. And so maybe we're taking like the vector sum of those to get a longer force vector than either one of those. Okay, so we're not just going to subtract these two forces. They're vectors. They have their forces, so they point in a given direction, and so we have to add them as vectors. And so yes, that gives us something longer than, for example, A. So does anybody disagree with that and think that there's a different configuration that might give us stronger force? Okay. Then let's fill in the gaps. Let me ask this. Between A and E, A has 3q of charge pushing up, and this has 3 separate charges. What direction do you think the test charge here is going to feel a force pushing it? It's going to point straight up. Just from the symmetry, you can see that the 3 force vectors are all going to have upwards components. So what's going to be bigger? The force on the charge here or the force on the charge here? A or E? I heard an A. Do you want to explain? Okay. Okay, I like that answer. Bringing things back. Okay, so you're saying that in A, sort of just all 3 charges are producing a force in the same direction, whereas in E, the outer charges are going to have components of their force that cancel out, so they're not going to produce as great an effect on this test charge. Yeah, so that's correct. So A is going to be greater than E. And I think we can argue they're bigger than B and D because those are the smallest. How about F? How does F compare to E? They're very similar. Which one is going to produce a bigger force on the test charge? Yeah. I hear both E and F. Bella? F points straight. F points straight upwards. Is that correct? Is that what you're saying? Yeah. Okay. How about E? I think we were just arguing that maybe E points straight upwards too. In the back. Is it because the angle of the charges would be less on F? So the angle to the outer charges, I don't know if they're really, are they different? They're similar. It's kind of hard to tell if they're different angles or not. Certainly if we move these charges further out, like if there's an arc here, If we move them further out, they're going to have less vertical component. So I think I can understand that argument. In the back. Ooh. Okay, so for F, these charges here are further away than the side charges in E. And as a result, they interact more weakly, right, because of that 1 over r squared. So that's an argument why F would be weaker than E. So that would put F down here below E. And is that everything? 1, 2, 3, 4, 5. Yeah. So I'm comfortable with all those explanations, giving us B and D being equivalent, and F, E, A, and then C. Yes?
Question. So for E, you said that the two side charges, they cancel out, which the horizontal components cancel out, but the vertical components don't.
Yeah.
And since their vertical component and the charge is closer to the test charge than the one in A, wouldn't that mean E stronger than A?
Let's look at this. Okay, so here is the configuration for E, and let's draw the forces, the force vectors from each of the 3 charges acting on this test charge. So this is charge 1, this is 2, and this is 3. We have F1, F2, and F3. So F1, we could break into components. And F3, we could break into components. And we can see when we add these up, the horizontal components of F1 and F3 cancel. And so what we're really adding are 3 vertical vectors. Whoops. Let me try that again. All right, we're going to add this vector. This vector. And that vector to get our total force. And if you like, I can also include, this left and right vector in this vector diagram that these cancel out. So if we compare that to what we had with 3q on the bottom, that was A. We compare that to diagram A. Diagram A is going to have 3 times as large of a force vector F2. Okay, so that's going to be like adding up F2 3 times. So let me add 3 of those. So this was for A, and this is for E. So with that type of diagram, you can see that the net force on the test charge in A is greater than in E. And the reason, again, is that parts of these force vectors cancel out. Okay, so we use the principle of superposition, which is to say if we can calculate the force on a test charge from one object, and we can calculate the force on it from a different object, the total force is just going to be the sum of those vectors. So you're used to using the principle of superposition whenever you drew free body diagrams in Physics 50. And this is the same thing. We just did that. So you may be able to make an argument or understand what's going on without drawing the diagrams, but you can always draw these diagrams. Just add up the individual forces from each point charge, and the magnitude of each, the force from each point charge can be found from Coulomb's law.
Okay, so in general, when we're trying to quantitatively solve for the force on a charged object, we're going to follow a very similar procedure pretty much every time. So first we just sketch this out. That's going to include the location of all the particles, some label for how much charge they have, and usually identify some coordinate system so that we can talk about the x and y components. And then we pick the particle that we're finding the force on. In this example, it was that test charge that we labeled Q test. But we could ask, what is the force on the bottom charge, or the left charge? Whichever charge we want to find the force on, we have to identify that so that we know what we're talking about. And then we can use Coulomb's law to find the force on that test charge from every other charged particle in our system. Sometimes our system will have symmetry that allows us to cancel out forces from charges that are on equal and opposite sides, or to cancel out the components of forces, like we did here. Make an argument that because this system is symmetric around the y-axis, there can't be a force in the x direction. And if we can do that, that can simplify the math, because we can not bother to calculate forces in a given direction. And you can make a free body diagram where you draw the force vector from each charged particle on your test object, and that lets you add up those force vectors to find some net force. Now I say add up. If you have a discrete number of point particles, each one producing a force, you just add them up. If your charge is uniformly distributed over an object, which is often the case, when I had that Van de Graaff generator in here, the charge got distributed around the ball at the top. So it wasn't like there was one charge here and one charge there. There was a distribution of charge. So how do we add up something over a continuous distribution? Here's a math term for it. It's not series. Series usually is a sum of terms. What happens when the number of terms becomes infinite? Because the number of charges is spread uniformly over something. Think math 31, integration. Yeah. So we very often have to do integration, because in the real world, our charge typically gets spread out. And then it can be very easy to sort of calculate an answer and not understand it, because we don't really have an intuition for like how big electric forces should be. It was much easier in physics 50 when you calculate like how fast you need to throw a ball in order to get it to go through a basketball hoop. You know, you could compare that to your experience and know that like, okay, when I throw a basketball, it's a couple meters per second. It's not a couple hundred meters per second. It's not a couple millimeters per second. So we had some intuition in like mechanics that we probably don't have in electricity and magnetism, but we can still do some checks to see if our answer makes sense. We can check directions, because we should be able to make arguments about, okay, these charges are positive, these ones are negative, they should attract. Make sure that our answer reflects that. We can often make some comparisons to cases where we do know what to expect. We know what to expect between 2 point charges. If we have 2 positive point charges, they're going to repel. Coulomb's law tells us how much they repel. If one of those is not a point charge, but it is a big distributed charge on a sphere, well, then it's harder. We can't just say, oh, it's going to be kq1 q2 over r squared. But we can say, what happens if we get really far away from that sphere? It's going to look like a point. So you can take a limit and say, in the limit where we get far away, I know what to expect. So let's get a practice doing all those things. Let's start with one that has discrete charges, 4 identical charges placed on the edges of a square, where the side of the square is d. If we want to find the force on each charge, we don't have to calculate it 4 times. we can figure out the force on one charge and then use symmetry to tell us every charge should have that same magnitude of force and rotated 90 degrees in direction. Okay, so we're going to use some symmetry considerations here to simplify this. Because we have point charges, we're going to use Coulomb's law. And because there's multiple charges producing multiple forces, we're going to do some vector addition. So let's work this out. Here's my 4 charges, and let me pick one to be my test charge. Okay, so I'm going to pick the top left. And I expect that if they're all the same charge, the same magnitude, and same sign, they're going to be repulsive. So if this is charge 1, this is 2, and this is 3, F1 points this way, F3 points that way, and F2 points away from charge 2, and I drew it smaller. Why did I draw F2 smaller than F1 and F3? Jared? Because of R squared. It's further away, so it has less effect. Okay, I'm just kind of sketching these. These aren't necessarily to scale, but I want to include things that I do know, like F2 should be smaller than F1 and F3, F1 and F3 should be the same. Okay, so the magnitude of F1 is going to be K, Q1, Q2 over R squared. And I'm just plugging in some parameters that I know. I know that R in this equation is the distance between my charges. And between my test charge and charge 3, that distance is D. And I also know that every charge has a magnitude of Q. So that's Q and that's Q. So I just plug in capital Q twice. Okay, so K, Q squared over D. That's the magnitude. The direction I drew. So I don't need to do any calculation for the direction. How about the magnitude? Oh, that was, yeah. F3 is going to be the same thing. Because 1 and 3 are the same distance away. Yeah.
Why is it not D squared?
D is squared. Thank you. That.
Or F1 too?
Thanks. And now F2. Let me do F2. It's different, so I'll do it in different colors to make it a little clearer. It has a magnitude that's going to look like K times Q1, Q2, which are both capital Q, over the distance squared. And that distance is going to be square root of 2D. Just from the Pythagorean theorem, this is the diagonal of a square. So I'll leave that geometry to you if you want to calculate it explicitly. And that gives us KQ squared over 2D squared. So again, the denominator is squared. So I know the magnitudes of the forces and I know the directions. So to find the total force, I have to add them up. And I have to add them up as vectors, right? Because they're in different directions. So let me pick a coordinate system that might not be the most obvious, but I'm going to pick one that's at 45 degrees. And the reason that I do that is because then I can say the net force, which I expect to be up and to the left, is along y. And there's no x component. Right? So the x components of F1 and F3 cancel. So I only need to consider the y components. Right? So this is 45 degrees. And this is 135 degrees. And so I expect that the net force is going to be the sum of all the y components. Okay, so from symmetry I can say that. I don't need to consider the x components. Because again, the x components will add up to 0. And so the y components look like the magnitude f1 times sine of 45 degrees. F2 is pointing along y. And F3 is at 135 degrees from my x-axis. Okay, so KQ1, Q2 over d squared times sine of 45 degrees is 1 over square root of 2. For F2, I've got KQQ over 2d squared. So I'm going to bring that 1 over 2 into the this fraction over here, and it's the entire. There's no sign term to consider. And then F3 has a magnitude of KQQ over d squared, and sine of 135 degrees is 1 over square root of 2. So you can see that the term before these parentheses are all the same. I can factor it out. And I'm left with some numerical factor that I could simplify that a little bit or evaluate it numerically. I'm just going to leave it. I don't care about the final form here. But that net force, I just calculated the magnitude. To write it as a vector, I can say that it's in the y direction because I've defined a coordinate system where that's meaningful. Or I could say that it's pointing outwards from the center of the square, which has the same meaning. And so that's the force on this one, but it had the same behavior for the other three. That is an outwards force with the same magnitude. Any questions on that one? Okay. So I have an activity that I'd like you to work on again in your small groups. And while the LAs are handing this out, let me go over what I want you to do. We have this configuration where there's a charge right here, and there are 5 different points in space marked by these red X's. And the first question asks you to consider what would happen if you put a positive test charge, Q sub test, at each one of these 5 points, and to draw the vector that represents the force it would feel due to this positive charge here. Okay, so you'll have some vectors drawn at each of these 5 points. For part 2, you'll do the same thing, except the test charge that you're imagining is only half as charged. Okay, so as a result, you should get a different magnitude of force, and your vector should have a different length. For part 3, we have the same setup, but now we're going to imagine our test charge has the same magnitude as in 1, but opposite sign. So now it's a negative test charge. And in 4, I want you to go and look at the 3 diagrams you've drawn and try to make some statement about the ratio of the force vector to the test charge. Is there some meaning to that ratio? If you can figure something out, try to describe it in part 4. And work together with your nearest neighbors on this. Okay, let's discuss. Hopefully your diagrams are similar to what I've drawn. Were there any questions about the first 3? So for 1, your arrow should point outwards. The closer they are to the test charge, the charge Q, the longer they should be. For 2, they're half as long as in 1, but in the same direction. And in 3, they're in the opposite direction as 1. So what can we say about the force that the charge feels divided by the magnitude of the test charge. So question 4. Does anybody have a thought? The ratio doesn't change. Let's see if that's the case. So let's say right here we put in, let's say it's 1 Coulomb of charge as our test charge. And we get this large outwards force. Here we put in half a Coulomb of charge and we get a smaller outwards force. But the ratio of that force divided by 1 Coulomb, and this force that's half as big divided by half a Coulomb is the same. Over here, the force points in the opposite direction as it did up here. Okay, so the force is the opposite, but the test charge was not plus 1 Coulomb, it was minus 1 Coulomb. So the ratio is the same. And that ratio is biggest the closer we are. Right? That ratio sort of tells us like how big that vector will be. As we get further away, it's smaller. And that ratio, we should also consider the direction. It's always pointing outwards. Right? And that ratio has a name. It's called the electric field. Okay, so the electric field tells you what the force would be on a positive test charge if we were to place a positive test charge at a certain location in space. Okay, so this is our expression for the electric force due to a distribution of charges. So Q sub j represents the jth charge in a distribution, and we're going to add up all of those j charges to find the force on charge I, which is what we're calculating here. So I know the math can get a little bit ugly and messy and look involved, but that's all that's saying. So this is the force on some charge due to all the other charges around it that we add up. And each one just contributes something that looks like Coulomb's law, and I should have a little r hat vector in there. That's an error. Okay, so if that's the force that a charge q sub I, our test charge, will feel at a certain point in space, then we can identify all the things in this expression that aren't related to q sub I. They're related to the surrounding charge distribution. And those things there we go, can be factored out. And if we do that, then we get an expression for the force on some test charge that if we first calculate this sum, once we know that value, whatever test charge we want to consider, we just multiply it by that to get the force. Okay, so presumably that would be something useful to know. If we know what the effect of all the surrounding charges is at a point in space, then we can very easily figure out what the force on any given charge at that point in space is. And we call this here the electric field. Okay, so we give it a name, and then we can just say the force on a charged particle is its charge times the electric field at its location in space. Okay, so we've actually done something similar to this before. Remember that this expression for Coulomb's law, if we go back, looks a lot like universal gravitational law, gmm over r squared. But when we want to calculate the weight of an apple, we didn't look up the mass of the Earth, the distance from the center of the Earth to our apple that's 1 foot off the table, right? We just said mg. That little g, that 9.8 meters per second squared that we used, essentially was the equivalent of the electric field. It was the contribution from all, I have to go through the end. It was the contribution from all the mass around our apple, let's say. So in mechanics, when we deal with gravity, this would be little g. This would be the acceleration due to gravity. You calculate it once, and then you just use it over and over. And it doesn't depend on the mass of the object you place in the gravitational field. Likewise, the electric field is independent of the charge that you place in the electric field, but is useful for calculating the force on that charge. So one way that we can visualize the electric field, and that's a very useful thing to do. If we can visualize the electric field, then we'll instantly know what the force on a positive test charge would be at different points in space. So we could take some distribution of charges. Let's say we just have a single positive charge. We could pick a point, much like we just did in that exercise, that handout, put a little x there, and say, okay, what is the force on a 1 Coulomb charge? Oh, it's a vector that points outwards. If we go further away, it's a smaller vector that points outwards. So we could draw a bunch of vectors in this area, and that would be an electric field diagram. Well, it gets complicated to draw lots of little vectors. So sometimes what we do is we pick a point, we say, what direction is the electric field? Okay, it points outwards. So let's move out a little bit and ask again, what direction is the electric field? Still outwards, so let's keep drawing outwards. Let's just follow a line in the direction of the force vector, and we call that an electric field line. And so here's what the electric field lines would look like. For a positive point charge, they're going to point outwards at every point. And so what this means is that at any point, let's say a little dot there, at that point, a positive test charge will feel a force in the direction of this line. So radially outwards. At this point up here, it will feel a force that's also radially outwards. We know that the closer we are to our charge, the greater the force would be, the stronger the electric field. And what in this diagram can you see that changes the closer we get to our charge? Because I no longer have individual vectors with different lengths. These are just continuous lines that have arrowheads to indicate the direction, but they actually just keep going off to infinity. So these aren't vectors. But what here in this diagram do you think I could use as a proxy for the magnitude or how strong the electric field is? What's greater in here than up here? Yeah.
Well, like the lines are closer together.
Yeah, the density of the lines we can use as a proxy for the strength of the electric field. So if they're closer together, that represents a stronger electric field. And if they're further apart, that represents a weaker electric field. So in these diagrams, we always want to draw our lines sort of starting on positive charges and equally distributed in all directions. And if we just have a positive charge, those lines will go out. If we had a negative charge, the direction flips and they come inwards. So electric field lines start on positive charges, they end on negative charges. And so if I have both a positive and a negative charge, my field lines near the positive charge look a lot like this. They start by pointing radially outwards. But you can make an argument that, say, at any point along this line of symmetry, the vectors, the force vector that a positive charge here would feel, one points down and away from the positive charge, and one points up and towards the negative charge. And so the net force would be horizontal. So the field lines should curl over and be tangent to a horizontal line along the center line. And these lines start on the positive charge, they end on the negative charge. The field is strongest close to either of the charges, and it gets weaker as we get further away because the lines get less dense. We can consider what happens if we have two positive charges. These field lines sort of repel each other. If you think about them, I mean, they don't actually interact, right? These are just concepts. But it's as if they're repelling each other. They won't cross. They can never cross. Why can two field lines never cross? Can you think of a logical argument, Bella? You're saying attractive or they do repel each other. I mean, they sort of interact in a way that they like move apart. But there's a logical reason why we can say they have to be like that. Yes.
Because if you have two different electric field lines intersecting, then at that point, since the direction of the force is tangent to those lines, then you have two different directions at the same point, which is impossible.
Yeah, exactly. So these field lines tell us the direction of the force that a positive 1 Coulomb test charge would feel. And so if you place a charge at some point, it can only feel a force in a certain direction. There's a uniquely defined direction. There can't be two different directions that it will feel a force simultaneously. So there has to be a given direction for the field line at that point, so we can't have field lines cross. Okay, so let's play around with these field line diagrams a little bit. I'm going to give you a chance to make your own in 3 dimensions around you. If you pull out your phone and scan this QR code, you can use your camera app to do that, and it will take you to the Zapper app that you should have downloaded last time. If you didn't, you'll be prompted to download it from the App Store. So once it loads this augmented reality experience, you'll get a little sheet explaining what you're going to be looking at. You hit the X in the top right corner to dismiss that sheet. And then you'll have a button to add a positive charge and a button to add a negative charge about a foot in front of your phone. So you can move your phone around and you can place charges in the environment around you, and you can look at the electric field lines that they produce. So one thing you can see is these field lines extend in 3-dimensional space, right? When I'm drawing them on the board, it's sort of all 2-dimensional, but really they're 3-dimensional things. Ah, yes. There's an Easter egg if you point out. So you can experiment with this with different charge distributions. A single charge is easy. 2 charges we sort of drew on the board. But you can think about like what would the charge distribution from that initial problem we did with 4 charges on the corners of a square look like. And you can test your hypothesis with this. Okay, so I'm going to bring you back to the projector here. And we're going to try to use Coulomb's law to calculate the force at a point, or actually we'll calculate the electric field. It's basically the same calculation, we just don't include the test charge in the calculation. But this time, instead of having a discrete number of particles producing this electric field, we're going to have our charge Q distributed along a rod. Okay, so we've got a charge rod. Its length is 2a, goes from minus a to plus a. And we're going to calculate the electric field some distance x away from the center of the rod, okay, in the perpendicular direction. So calculating this involves carefully drawing a picture in setting up the calculation. We're going to use Coulomb's law, but because our charge is distributed, what we have to do is we have to consider one little chunk of charge. And when we deal with little chunks of things, we call them differential elements. So instead of a charge Q, we're going to have a differential chunk of charge dQ. And this is just some representative element. So it's going to be at some vertical position that I'll call y. And I'm interested in finding the electric field out here at some distance x. So I know that the magnitude of that field depends on r, and I know that r is related to x and y through the Pythagorean theorem. So what I want to do is I want to say that there's this electric field, dE. So the D here means there's a little bit of electric field coming from this little bit of charge. So if I have a D here, and the charge producing the field, but I'm not producing, this is not the entire electric field from the rod, it's just a little chunk of it. So when I have a little chunk of something, I put that D in there, right? So you see there's going to be some calculus involved. But I can write an expression for the magnitude of that electric field. It's just K times the charge producing it. If it were a force, I would multiply it by the test charge and then divide it by r squared. But I'm not going to include the test charge in this calculation because I'm not calculating a force, I'm calculating an electric field. Okay. Otherwise, it's identical to the Coulomb's law calculations. Okay, so that's the electric field from that little chunk. If I want to get the total electric field, I just have to add up all the little bits of electric field. That means I have to integrate dE. So let me just add in a few little details here, my vector notation to tell me direction. Okay, so I'm going to have to add up a bunch of different vectors, right? As I move this little chunk dq up and down the rod, I'm going to go all the way from minus a to plus a, and at each point, this dE is going to point in a different direction. So let me see if I can use the symmetry to make an argument about what direction the total electric field has to point. What do you think? Over here, I put a positive test charge, and I have positive charge distributed on this rod. What direction do you think the force will be on that positive test charge? To the right. Okay, so it's going to be repelled by this positive charge. So the electric field should point to the right. What about, should there be a vertical component? No, because of the symmetry, right? For every little chunk in the bottom that's pointing up and to the right, there's a chunk in the top that's pointing down and to the right. So by symmetry, I expect the y component to be 0. So I only need to calculate the x component. Okay, well, the x component is going to come from integrating the x component of the electric field. So let's see what that is. Here's the x component. Just for completeness, here's the y component, which I'm not going to care about. So I'm making the argument that the y components cancel. So, normally what I would do is I'd say there's some angle, and I would say that the x component is related to the magnitude by the cosine of that angle theta. So that angle theta is the same as that angle theta. And the cosine of that angle must be x over r. Because I have a right triangle with a side x and a hypotenuse r. Okay, so putting that together, My dE, I've got an expression for right here. My cosine theta is x over r. And other things that I can substitute. I've now got an r cubed in the denominator and an x dq in the numerator. So let me use the fact that r is square root of x squared plus y squared. I will leave my x the way it is. I'll leave my k. And dq, this is the thing that I'm integrating over. I haven't included it yet. I need to rewrite this dq over here, but I need to write it in a way where I can do this mathematical integral. That is, I need to relate dq, the little chunk of charge, to where it is on this stick, so that I have a variable that I can integrate over. So I'm going to use the fact that the charge is distributed evenly. That is to say, the fraction of the charge that's within that little element dq is equal to the fraction of the length of the rod that's within that little element. So another way of saying that is q over 2a. So if I solve this for dq, I get this q over 2a. That's the linear charge density. It's the amount of charge per unit length. I put a charge of q onto a rod of length 2a, and it distributes uniformly. So there's q over 2a coulombs per meter of charge. So in this little element that's dy thick, that many meters thick, this product is how many coulombs are contained in it. And that's what I'm going to plug in then over here for dq. So now I've got a lot of things that don't depend on my variable of integration. And my variable of integration is y. I'm going to integrate over y from the bottom of the stick to the top of the stick. And that means from minus a to plus a. And anything that doesn't depend on y, I can factor out. So k, q over 2a, and x don't depend on y. And I'm going to write this slightly differently. The denominator I'm going to write as x squared plus y squared to the 3 halves, which is the same thing as square root of x squared plus y squared cubed. And the reason I do that is this integral, I can solve that using trig sub. It's another page of work. I'm going to skip that page, and I'm just going to quote the results that I can also look up. So a lot of these integrals are things you can just look up in an integral table. That's what I've done here. I'm going to use the fact that that integral equals, let's see, in black there, you can see an analogous integral that gives me the result that I'm after. So when I do that, I'm going to get a y over x square root of x squared plus y squared. Right, so that term in parentheses is the evaluation of the integral, and I need to evaluate it at the limits of minus a and plus a. Right, and remember that it's y that I integrated over, so I'm replacing y with plus a and y with minus a. So I've got all the stuff that came before the integral. And now when I plug in plus a, I get the first term. And then I subtract what I get when I plug in minus a. And I can simplify this. Because if I look at these two terms, they're identical, right? This minus a squared, the minus sign just goes away. So the denominator here and the denominator there are the same. And then I've got a minus negative, which is positive. So I end up with a plus a, or 2a, in the numerator, which will cancel out the 2a that I had in the denominator right there. And I still got the x times square root of x squared plus a squared. So if I try to interpret this result, here's another cancellation. The x's cancel. I see the x canceling, but I don't think there should be an x canceling. Oh, so sorry. Yeah. Actually, I made a mistake. I'm going to correct it in a moment. But first, let me show you how I figured out that I made a mistake. When I simplify this, here's the expression that I get. And I want to remember what I was calculating. I was calculating the electric field at point x. And I said there was no y component. It was all along x. And this was the magnitude of the x component. So I can write this as a vector pointing along x. And I can ask if this makes sense. And it doesn't. So let's try to understand why. I can compare this to Coulomb's law. Coulomb's law tells me that the electric field from a point charge looks like k times q over r squared. Right? When we had Coulomb's law, we just multiplied both sides by q to get a force. And it was kq1, q2 over r squared. So for a single point charge, this is what Coulomb's law tells us the electric field is. Let me compare that to what I calculated here. In particular, I've got my charge distributed over a rod of length 2a. So let's say this meter stick is my rod. I fill it with charge, and then I stand far enough away from this, it's just going to look like a dot. And so if I do that, if I'm far enough away, this should be the same thing as that. And it's not, because if I'm far enough away, a becomes negligible. The square root of x squared is just x. My answer just has an x in the bottom instead of an x squared in the bottom. So I know that my dimensionality is not correct. And in fact, what I messed up was in this integral that should be squared. So there should be an x there. Okay, so we went a little bit over. I apologize for that. We'll wrap up here, and then I will see you on Thursday.